All right, in this video, we'll be covering electron configurations and we'll be going over what those are. So we'll start off by asking the question, what are electron configurations? So if you look over here on this part of the table, you can see an example of what an electron configuration looks like. And so these are just a systematic way of showing how the electrons are distributed throughout the orbitals in an atom. And so they use the quantum numbers. So those are covered in another video. But as you know, that this number that comes before the letter represents a quantum number. The letter itself represents a quantum number. So they take advantage of those and they show where the electrons are placed. And so the electrons are these numbers up in the top, like the exponents. So they tell you how many electrons are in that specific orbital. So if you see like the 1s orbital, we have two of them in this example. But in the 2s, we just have one electron in that orbital. And so the way that these are arranged is you put them in order of the lowest to highest energy. So we have like the s, the p, the d, the f orbitals. Then you also have your different energy shells. And so those will come into play as well. But you can see here an example of just how in each situation, you have them in order. The 1s is always first, and the 2s, the 2p, and then the 3s. So this next slide shows what the order of filling these orbitals looks like. And so you go start from the bottom and you work your way up. So in this case, I have this chart over here that shows the order of the fillings, and it has the 1s on the bottom because that's the lowest energy level, and then it increases. And as you can see, some of these numbers don't really fit with each other. Like I have a 3 here, and then a 4, and then a 3. There's a 5 and a 4. Come up here, there's another 4. There's a 5 all the way up at the top. And so they're not all in order by the numbers because they're based off the energy level. It's not necessarily the number that's in front of it. So one way that you can keep these in order is by this little diagram here. And as you go through here diagonally, it helps you understand what the order of the electron configurations are. And so this is something that, it's helpful to memorize, but as we'll go further in this PowerPoint, the periodic table is also a helpful guide to discovering the order of these orbitals. And so these different subshells, they hold different amounts of electrons in them. So like the s orbitals can hold a maximum of 2, while the p orbitals can hold up to 6, the d orbitals can hold up to 10, and then the f orbitals can hold up to 14. And so these start to overlap once you get going up higher and higher in the energy levels, because the energy levels will get closer and closer to each other. So as I mentioned before, here we have our periodic table. And in this diagram, you can see that we have some of the electron configuration things put inside the table. And so the way you can use the periodic table as a guide is reading it like you would a book. So you start at the top left, and then you read towards the right, and then you move down a row, and then you go towards the right, and you move down a row and onward until you get to the specific atom that you're trying to find the electron configuration for. And so the columns are also helpful, or the groups are helpful in knowing what the subshells are. So in these first two groups, we have the s orbitals. And then come over here, you have the p, in the middle where the transition metals are the d, and then in the lanthanides and actinides, you have the f. So as you go through, you can see it goes from 1 to 2, down to 3, and then to 4. But after 4s, when you move into the transition metals, you hit a 3. So even though 3 comes before 4, in this case, the 3d is higher in energy than the 4s. So because the 4s is lower, it will come first. So as you go from left to right, you'll fill in the 4s orbitals before you move into the 3D ones. And then as you go onward, it jumps back up to 4. And then later, when you reach the lanthanides and actinides, these have the F, as you can see, but they're also 2 lower than the row that they're in. So if you're in the 6th row here, that correlates to the 4 here, and the 7, and with the 5. And with the transition metals, it's a similar thing. The number you have here is just 1 less than the number you have in the row. So if it's a 4 here, it'll be a 3 there. And so this is a helpful way as you're going through, if they give you an atom to find the electron configuration, just isolate where it's at and then begin going left to right and reading it and filling it in. So on this next slide, I have an example of what that looks like. So if it asks, like, what is the electron configuration of sulfur? So first we locate where sulfur is. It's right here. And so we start up here at the top left and we work our way down to the right. So we'll fill this 1s and then this one. Then we fill both of these 2s, move on to the 2p, fill all of those, move down here, fill up the 3s. And then when you come over here, you work your way over until you reach the sulfur. So in this case, we have 2 in the 1s, we have this one and this one, 2 in the 2s, 6 electrons in the 2p, 2 in the 3s, and then 1, 2, 3, 4 here in the 3p. So here you can see that this is the electron configuration for sulfur. And then as another example, I've included zinc, which is one where you run into the transition metals. So it's the same process. You go through past sulfur and keep going. And then you have to keep in mind also that this 3D is higher in energy than the 4s. So when you're writing it, you'll have that 3D afterwards. And so zinc is over here at the end of that transition metal row. So it has 10 electrons in the 3D. And as you keep going down the periodic table, obviously these will get longer and longer and longer. So I've included this one, moscovium, which is down here in the periodic table. And you can see here that this is what the electron configuration looks like. It's really big, that's a lot to write, especially if you don't have a lot of time. And it's easy to mess this up and put the wrong numbers, the wrong letters. And so there's an easier way that we can write these configurations, and that is using the condensed versions. And so down here at the bottom, I've included barium. This is the electron configuration for barium, which is located here on the periodic table. So you can see that this is the expanded version. If I write this out, it's kind of a lot, but with the condensed version, it shortens down to just this. It's a lot more simple than writing all of this out. And so the way you can find these condensed ones is you locate the atom you're looking for, the element. And so then you go back to the noble gas that comes before it. So in this case, on this row here, barium. So move back to cesium, then move back one more, get to xenon. So that noble gas that comes before whatever element you're looking for, you can put that noble gas in these brackets like I did here. And this basically says that I have the electron configuration for everything that comes before xenon. So all of this stuff that I would put here, I can just shorten that down here. And then what you put after is just the things that would come after xenon. So in this case, if I have this configuration and I want to go to barium, let's drop down here. This is the 6th row down, and this is group 1 and 2. So these will be S. And so 6s1, 6s2. And then all I do is put that 6s2 after the xenon, and that gives you the condensed version. So this is a lot simpler to write, doesn't take up as much room. And you just take the noble gas and you add the remainder of the electron configuration after that. And so with these electron configurations, you can use them to fill out orbital diagrams. And really the orbital diagrams can also help you figure out like the electron configurations. And so for these, they'll show you where the electrons are placed. So once again, I have this display here of the order of the energy levels. And so you start your way up from the bottom and you work your way up. And in these, it's based off the number of electrons you have for that element. And so, like obviously the ones that come earlier in the periodic table will just occupy these first ones. But as you work your way up, you have more and more. And one thing to keep in mind as you're doing this is that you use arrows to represent the electrons. And in each one of these boxes, there can only be a maximum of 2. And there's another important thing that goes along with that, and that's Hund's rule, which means before you double up, before you put 2 electrons in the same orbital, you need to occupy all the orbitals first. So let's say I have these 3 electrons in the 2p. I'm going to put 1 in each of these orbitals before I put 2 in any of them. So in this example down here, it's wrong because this arrow should be over here and it should be pointing up. All the arrows should be pointing the same direction and they should all be in different orbitals. And so as you can see in these ones, there's a maximum of 2. One is up, one is down, which represents spin up and spin down. And so you need to pair these up together only when all the other degenerate orbitals, or the ones of the same energy, each have an electron in them. And so just a quick example with this, it says fill in the orbital diagram for oxygen. So here I've included the electron configuration for oxygen. So it's 1s2, 2s2, 2p4. And then also just to make it simple, I wrote 8 electrons. That's how much oxygen has. And so in this chart here, like let's say you know that there's 8 electrons. I'll switch over to my pen. So I'll start from the bottom and work my way up. So I start here with the 1s. So I start by putting a 1 up. And then because this is the lowest energy, I can also put 1 down. I can put 2 in that because there's none that are the same energy level that need to separate them into. So I have 2 here. I'll go up to 2s, and I have 2 there also. Spin up, spin down. But then here, when I get to the 2p, I have 4 remaining electrons that I have not put in any of these boxes yet. And so before you pair them up, you need to separate them. So I have put 1 here in this box, 1 there in that one, 1 here. And then with the last one, you just toss it in this, and it has a spin of a different direction than the other ones. And so that is what the orbital diagrams were used for. You can put these electrons in here and see how much you have. And then, like, let's say I didn't have the electron configuration, then I could use this information that I have, and they can look at this and say, okay, I have 2 electrons in the 1s, I have 2 here, in the 2s, and then 1, 2, 3, 4 in the 2p, and then I can write it like this. And so the orbital diagrams are just a helpful way to both visualize it and then put it into practice. And so another thing to keep in mind is that with ions and transition metals, there's some things that don't necessarily follow the rules that we've covered so far. And so we'll start off by talking about the electron configurations of ions. So in this picture over here, I have the ions of oxygen, fluorine, neon, sodium, magnesium. And all these ions here, if you look at the neutral atom, so what it is when it's not an ion. So this is the electron configuration. It's they've removed the 1s ones here just to make it shorter. But you can see here that each one of these has a different electron configuration because every neutral element has its own unique electron configuration. But with ions, remember that you lose or you gain electrons because these elements want to have like the same configurations as a noble gas because that's most stable. So this oxygen, if it's losing 2 electrons, that means that if it's gaining 2 electrons, excuse me, that's what the negative means. If it's gaining 2 electrons, that means the configuration is going to change because the amount of electrons no longer matches what it was initially. So with fluorine, I'm gaining 1, so that means this has to change. And then for these cations, when you lose the electrons, then the configuration goes down. So the interesting thing is that all 5 of these here, so these 2 anions, these 2 cations, and then the noble gas, all of these have the same electron configuration. So these are called isoelectric, which means that they all have the same electron configuration. So when you do this, you need to keep in mind what the ion is, so how many it gains or loses, and then as you use the periodic table, you can either like move forward a couple to get to the noble gas if you're an anion, or for the cation, then you move backward a couple, and then you get to the noble gas. And so this is a helpful thing to keep in mind as well, because ions they can be different, and as you can see here, even the sizes are affected by the electrons that are gained or lost, which is something that will be covered in a different lecture video. But just to keep in mind that when these ions, when they lose or gain electrons, it changes their electron configuration and also their size. And then another thing that's important to keep in mind is regarding transition metals. So with transition metals, those are the ones in the middle of the periodic table with the D ones. And so if you look over here at these, we've learned from the previous slide that the 4s is lower in energy than the 3d. So that means the 4s ones will fill up first. So that's the case you see here. You fill up the 4s and then you throw them in the 3d. But then when you come down here, you see that changes. Now it's only 1 here in the 4s, but there's 5 here in the 3d. If you keep on going, you'll see it again down here. And so what's happening in these situations is that so you can fill up that 4s with the 2 electrons. As you move into the 3d, it actually represents a lower energy level when you have all of those 3d orbitals either half filled or completely filled. So to make that seem a little more clear, I have this picture of the periodic table. So you can see this is the 1, 2, 3, the 4th row over into the transition metals, the fourth column, I guess. And then this one is the 9th. So if I'm filling up, we're doing my electron configurations. I come here first before I get down here. So this is 4s, so 4s2, and 3d, 1, 2, 3, 4. But if I take one of these 4s and move it into my 3d, then I can have 5 in the 3d. And so that means each one of those 5 orbitals for 3d would each have 1 electron in them. And so that is energetically more favorable to have those than to fill up these 2 with the 4s and then just only have 4 here in the 3d. So if you go to the 4th column over and then the 9th column over here, in these situations, you'll just have 1 in the 4s or in the 5s, depending on which row you're in, and as it goes down onward. But then you actually fill up those D1s first. So if you look back here, you can see you have a 10 and a 5 here. So this is half full, this one's completely full. And with the half full and the complete full, you see that there's just 1. But then, like if you go in here, like let's say you have zinc, then the 3D is completely filled. So both the 4s and the 3D would be filled. So you don't have to worry about that exception. But that's just something to keep in mind, is that for those transition metals that are in the 4th column over the 9th column, they're going to take one of those 4s electrons and then put it into the 3D just to make it more stable. And so that is all I have today about electron configurations. I hope this makes sense and that you continue to do well in chemistry, because it gets a lot more difficult from here. But thank you for watching, and I hope everyone has a good day.